Cheng. Today we're going to be doing diffusion and osmosis and water potential. So what is diffusion? I'm going to have a simple example to explain what diffusion generally is, and we'll apply to the biology level in a second. So let's say a woman in the corner of the room sprays her perfume. That perfume is an aerosol, which means it is a bunch of gas particles released after it's sprayed. So how does the kid in the corner smell it after, let's say, 10 seconds, 10-15 seconds? Right when you spray it, there's a very high concentrated amount of the gaseous particles near the girl where she sprayed the perfume at. Of course, these particles have a natural affinity to reach equilibrium after bouncing off each other multiple times, because as you know, all particles are moving, especially at a gaseous state where energy is high. So as time goes by, we're speaking matter of seconds, the particles will bounce off each other and spread out across the room until equilibrium of the particles are reached, as you can see here. And then this enables the kid in the corner to smell the perfume, because clearly it is diffused throughout the entire room in an equal pattern. Now let's talk about active transport.
Alright, so a quick reminder, in passive transport, we're moving substances from higher concentrations to lower concentrations in order to achieve equilibrium. But now, since we're talking about active transport, it's kind of the opposite. We're taking particles from lower concentrations and moving them to higher concentrations. So it's against the concentration gradient. So this process, actually, it requires energy, and that energy is found in forms of ATP. If it uses chemical energy, we're going to call that primary active transport. And if we're just using ATP, that's secondary or co-transport. Alright, so now I'm going to talk to you guys about osmosis. So as many of you have probably seen Osmosis Jones. That shows. Alright, so basically, osmosis is defined as the net movement of solvent particles through a semi-permeable membrane in order to reestablish equilibrium of solute molecules. So basically, equal molarity on each side. And we define that as isotonic. So a solution's isotonic if the molarity is the same on each side of the semi-permeable membrane. Okay, so what's going to happen is I'm going to draw some solute particles on each side. So there's 5 on this side, and there will be 3 on this side. So what's going to happen is water tends to flow towards concentrations of greater molecules, or in this case, and talking about relativity, this would be hypertonic to this, which is hypotonic, which means it has less solute molecules, and hypertonic means it has more solute molecules than the other side. And so water tends to flow towards the more concentrated solution. So since we have more solutes here, water will flow in this direction. And this will change the water levels here. So now what we're going to have is a lower water level on the right side and a higher one on the left side. This is because osmosis is trying to reestablish an equilibrium and have equal concentrations of solute on each side. So adding more water evens out the molarity, it dilutes the solution, so the molarity would be the same on each side.
Water potential is the quantitative measurement that determines the direction of movement of water, and it's measured in units of megapascals, MPa. And water will move from higher potential to lower potential. The word potential is actually potential energy, water's potential energy. Just as a ball at the top of Mount Everest has potential energy to fall, water has the same concept, conceptually, the same potential energy to move in or out of the sun. So what affects water potential? Well, we mentioned before, solutes and pressure. And we're going to call that solute potential, and pressure potential. And that will make water potential. Solute potential plus pressure potential is water potential. So we've now discussed solute potential and pressure potential separately. So let's combine them together back into some application. So here is an example of a U-tube separated by a semi-permeable membrane. This allows only water to pass through as solutes are too big. And so these lines indicate the water level. And here, water potential is 0. You can indicate that as psi W is 0 MPa on both sides, from the left side and the right side. However, if I were to add solutes to one side, let's say I add solutes to the right side, this will therefore decrease the solute potential because solute molecules bind to water molecules, and by decreasing, let's say this is a 0.2 molarity, by decreasing solute potential, we are therefore dropping the overall water potential, and as a simple, easy example, I'll say negative 0.3, because the solute potential is also negative 0.3, actually negative 0.2. Negative 0.2. And this will cause the water potential here to be negative 0.2, while the water potential here on the left side is still 0. And so since water flows from the high potential to the lower potential, water will flow in the right direction, and therefore water will increase on the right side and decrease on the left side. Noticeable. Okay? But what happens if we add pressure? So let's see, this will be our fake plunger, for example. This thing, we will stuff that onto the right side and increase the pressure potential on the right side. So let's increase this pressure. So I'm going to smash the water back down to this level. Maybe a little lower. Down here. And therefore I'm increasing the pressure potential, and pressure is going to be positive here because I'm applying positive pressure. I'm increasing the pressure potential, psi p, to be, let's say, 0.3 MPAs. And so when you add negative 0.2 and 0.3 together, the total water potential would then become 0.1. And so 0.1 is now greater than 0, because 0 is obviously less than 0.1. And so water will flow from obviously higher potential to lower potential, and water will then flow back to the left side because of the increase in pressure. That is a practical application of water potential.
So this concludes our presentations. I'm Danny Cheng.
I'm Neil Rastogi.
And I'm Eddie Lai, and I hope you've enjoyed our presentation on water potential and diffusion.
And active transport.
Bye!
Or turgidity or turgidity, I don't know how to pronounce it. But anyways, okay, what is diffusion? I have a simple example for you guys. So basically, say we have a kid in the corner of the classroom, right here, and he cuts the cheese. The gas released by his anal sphincter.
We're done. Alright, we need another example.
What?
I didn't draw the same thing.
You didn't, because you're dumb.